To begin, what is radiation? Radiation is the emission or transmission of energy in the form of waves or particles through space or through a material medium. Last year, we learned about ionizing radiation, which is a type of radiation with enough energy that it can remove tightly bound electrons from the orbit of an atom, causing the atom to become charged or ionized. Ionizing radiation can occur when the nucleus of a radioisotope spontaneously changes its nuclear structure, or disintegrates, releasing energy. This process is known as radioactive decay, and occurs when the electrostatic forces within the nucleus, which is the force of attraction or repulsion due to electric charges, overcomes the strong nuclear force, which is the force holding the nucleus together. As you may remember, there are 3 types of radioactive decay: alpha, beta, and gamma. In alpha radiation, an alpha particle is released from the nucleus, which resembles a helium nucleus in structure. In beta decay, an electron or a positron are released. In gamma decay, gamma rays are released, which are highly energetic electromagnetic rays emitted from photons, which are particles of light. Now that you are familiar with the notion that radiation takes the form of subatomic particles, such as electrons and positrons, and waves, such as gamma rays, let's talk about a new type of radiation: blackbody radiation. You may remember the electromagnetic spectrum from optics, with everything from deadly high-energy gamma rays to harmless radio waves. A blackbody is an object that absorbs all frequencies of electromagnetic radiation. Because absorbing this much energy would cause the object to heat up forever, the object emits radiation to maintain its temperature. The blackbody emits electromagnetic radiation of all wavelengths, meaning that blackbody radiation is the radiation emitted by these objects. The sun is the first example of a blackbody. The sun emits radiation of all electromagnetic wavelengths. However, most of the radiation emitted by the sun is in the visible spectrum, which is between 400 and 800 nanometers. This is why our eyes evolved to pick up this kind of light. The blackbody spectrum depends only on temperature. As the temperature of an object rises, the wavelength that is emitted at maximum intensity, which is essentially maximum power, will shift to the left with respect to the spectrum. This is represented by the peaks of the curves shifting to the left of the graph as the temperature of the object rises. Simply put, the hotter the object is, the more it will emit radiation closer to the left side of the spectrum. This maximum intensity will move into the visible spectrum at around 4,000 Kelvin or above, which makes sense because the temperature of the sun is 5,800 Kelvin. This means that because of the sun's temperature, most of the radiation it emits is between 400 and 800 nanometers. This is why very hot objects appear to glow. Their hot temperatures cause them to emit a lot of visible light, because the wavelength that is emitted at maximum intensity is in the visible light spectrum. In contrast, objects with low temperatures, such as the human body, which has a temperature of around 37 degrees Celsius, emit practically no visible light, because their low temperatures cause their wavelengths emitted at maximum intensity to not be in the visible light spectrum. This is why we can't see each other in the dark. The problem with the blackbody spectrum was that classical electromagnetism could not account for it. Mathematical models attempting to produce these distributions were able to fit the data for the longer wavelengths, such as infrared or radio waves, but were unable to predict that shorter wavelengths would decrease in intensity. Scientists assumed that because frequency increased, energy increased, meaning that intensity should rise exponentially. Simply put, according to classical physics, the blackbody should emit infinite amounts of UV radiation. This can't be true, because this would mean that every time you used a heated appliance, such as a toaster, you would be subject to a fatal intensity of UV and X-ray radiation due to the object's high temperature. This would also violate the law of conservation of energy. This contradiction was called the ultraviolet catastrophe, because of the conflicting data for the UV portion of the blackbody spectrum. The ultraviolet catastrophe led physicists to to the realization that classical electromagnetism must be incomplete. In 1901, German physicist Max Planck solved the UV catastrophe by implementing a concept known as quantization. We learned last year that heat is the transfer of kinetic energy from one object to another. In a solid, such as a blackbody, this kinetic energy is generated by the vibration of the particles. When an electromagnetic wave hits an atom, the energy from the wave is transferred to the atom, causing it to oscillate or vibrate. It then radiates this energy back into the environment, generating the light we see in the blackbody spectrum. Back in Planck's days, they did not know a lot about the subatomic particles of the atom. Today, we know that when an electromagnetic wave interacts with an atom, the photons in the waves transfer their energy to the electrons, promoting the electrons to a higher energy orbit. As the electrons attempt to return to their original electron orbit, they emit a photon, which is where the radiation comes from. Planck proposed that the energy emitted by these vibrating atoms must be quantized, meaning that they must have specific values, not infinite values. The energy can only take on a discrete value from a set of expected values. Now that we know more about light, we understand this to mean that a photon can only contain specific quantities of energy. This is because the energy transferred to an electron from a photon that allows it to move up energy levels only allows it to release the quantity of energy that was originally absorbed. Using Planck's constant, Einstein created an equation that determined the energy of a photon at a certain frequency, E equals NHF, where E is the energy in joules, F is the frequency in hertz, and H is 6.63 times 10 to the negative 34 joules per second, which is called Planck's constant, which he determined by experiment. N represents the number of quanta, or photons, emitted. N can only be integers because you can't have 1.5 photons, for example, and therefore the energy emitted can only be whole number multiples of the minimum energy resulting from the emission of one photon, which is essentially H times F. Because N can only be integers, E can only take on specific values, which is what results in quantization. Let's try an example. A photon has a frequency of 2.68 times 10 to the 6 Hz. Calculate its energy. So we know that our givens are N equals 1 because in the question it says a photon, and F equals 2.68 times 10 to the 6 Hz. We also know that H equals 6.63 times 10 to the negative 34 joules seconds, because that's Planck's constant. Now we can use the formula E equals NHF and plug in our values to get a final answer of E equals 1.78 times 10 to the negative 27 joules. This equation allowed for the accurate prediction of the true distribution of blackbody radiation at all wavelengths, because it showed that an average wavelength of energy was released by the blackbody, and this average is released at maximum intensity. Because many less atoms will emit wavelengths above or below this average, the curve is shaped the way it is. This was so difficult to detect because the constant is so small. Energy released by a black body appears to be released continuously to a macroscopic being, but on a fundamental level, it is quantized, meaning that only certain quantities of energy are allowed to be released at a time. It is like the blackbody radiation is releasing small packets of energy at a time. These packets of energy were called quanta, which then became known as photons. Planck's equation and theory about quantization allowed us to develop the correct blackbody spectrum. This can be useful because since stars are black bodies, their observed color allows us to use the blackbody spectrum to figure out their temperature. Knowing the temperature allows us to calculate the amount of fusion that needs to take place to keep the star at this temperature, and in order to have this much fusion, we can work out how much mass is needed. This information can then allow us to calculate the size of the star, even if it's millions of light years away. Planck didn't know the true magnitude of his discovery at the time, but his work pioneered the field of quantum mechanics, as he was the first to propose that light was not only a wave, but a particle, introducing a chain reaction of theories that would follow in the years to come.